Thanks a lot for the opportunity to talk here. I'm a postdoc at the Ice and Climate Group in Copenhagen and also part of the TIPES Horizon 2020 project. And I want to talk about work together with Peter Ditlevsen on the risk of tipping the overturning circulation due to increasing rates of ice melt. In other words, rate-induced tipping of the AMOC. And so now everybody should be aware that there's at least a potential risk of a tipping point of the AMOC due to increasing freshwater into the North Atlantic as more ice is melting with higher temperatures. Now, while the true control parameter is, of course, the atmospheric greenhouse gas concentration, effectively, we can monitor the Greenland freshwater runoff as a control parameter, which I've shown here in the vertical axis. And if there would be such a tipping point, that means that beyond a certain critical threshold, the AMOC would collapse, and you have this unsafe area here, which I highlighted in yellow. Oops. Now, of course, as has been pointed out before, it's not really certain whether there is actually such a tipping point, and different models give different answers. And the purpose of this talk is not to constrain any further the likelihood of such a tipping point to exist, but rather to say that if we have such a tipping point, could there be other qualitative behaviors that might even further shrink this safe operating space? So in other words, could there be another regime, which I had it here in gray, due to rate-induced tipping, where a tipping would occur even before we pass this critical threshold? So on the horizontal axis here, I've plotted the Greenland meltwater rate of change. And if we would have a rate-induced mechanism, that would mean that even before crossing this threshold, if we change at a fast enough rate, we could still induce tipping. And at least if this is the case, we can already see in data, which is this colored trajectory here, that if such a rate-induced threshold exists, that we're approaching it, because the Greenland melt is actually accelerating over time. And now what we try to do is to see whether we can see such a mechanism in a global ocean model. And to do this, we use the VEROS ocean model, which has been developed by colleagues in our group in a present-day configuration. It has 2 to 5 degrees horizontal resolution and 40 vertical layers. So for climate modelers, this is pretty coarse resolution, but at least for dynamical systems experts, it's still a very large dynamical system with about 1 million degrees of freedom. And what we did now is similar to what Frank has been showing. So a freshwater hosing experiment where we ramped up a freshwater anomaly over the North Atlantic, which you can see here in the blue colors, very slowly. First of all, so here on this plot, you can see the AMOC strength as a function of this freshwater forcing parameter. And as we increase the freshwater forcing here in black, you can see that at some value, the AMOC collapses, and so does the AMOC, maximum AMOC strength collapses. And then as we decrease the parameter, it resurges at some point. So you have both a tipping of the AMOC, but you also have this range of bistability or hysteresis. Now, in order to check for rate-induced transitions, what we want to do is we want to move the freshwater forcing within this region of bistability by moving from one forcing value F1 to F2, which is still below the tipping point that we obtain in the quasi-stationary picture. And we want to do this at different rates and see whether we can actually still have a collapse, even though we don't go over the edge here. And now, if I choose a linear ramping as such, that takes 160 years here, we can see that the system is actually able to track the this quasi-stationary equilibrium here, and we don't have any tipping. But now if I go to a faster parameter change, a ramp of 140 years, you can see that we actually tip down to this lower branch, which is the branch of a collapsed AMOC. So we indeed see a rate-induced tipping in this model. And here I show the same thing, but just as time series. So you have a spin-up trajectory here with some multi-decadal oscillations, and then we branch off 2 realizations. One with a slightly faster rate where you tip down, and the other one where you can track this equilibrium here. So this suggests somewhere in between these 2 values, there could be a critical rate of tipping. And what we see is if we choose a rate in between, is actually this rather strange behavior where the trajectory doesn't seem to approach either of the two attractors. And this phenomenon is actually known in rate-induced tipping, where if there's a critical rate and you are close to this critical rate, your system state will be attracted by the stable manifold of a saddle that separates these two attractors and then approaches this saddle very closely and then stays there for quite a while until it's going to be ejected to either of the two attractors. And we believe that that's happening here. So what we now did is we systematically varied this rate of change over a whole range, which you can see here on the vertical are the different durations of the ramping. So in other words, the rate. And in the vertical, you have time, and the color-coded is again the AMOC strength. And in red here, you can see trajectories where the AMOC is collapsing. And what you can see is that for a slow ramping on the right, all of the trajectories are able to track the state. Whereas for fast ramping, most of the trajectories tip, but not all of them. And also in between, you can see some trajectories that do a little bit of different dynamics, as we discussed before, that are related to this saddle state, or I also call it edge state here. And this is summarized down here by this bar plot, where red colors indicate tipping, white colors tracking, and yellow colors the state in between. And what we can see is that there's actually no clear-cut boundary, so there is not a single critical rate of tipping here. And if you just change the rate of change slightly, you can go from a tipping realization to a tracking realization. So that seems to be very sensitive. And now if we thought if a very small change in this rate of change can make a difference, maybe also a small change in the initial conditions can. So what we did now is we fixed the rate of change and instead looked at different initial conditions. So here you see a rather arbitrary projection of the attractor into two variables. And what we do is now we sample this attractor, which is a long spin-up run in time to get different initial conditions. And now here again on the horizontal, you can see the different realizations or the different ensemble members. And down here, the time series, that's the attractor in terms of its AMOC strength. And what we now do is we branch off at different times realizations and then use the same forcing ramp applied to them. And you can see that only some of the trajectories actually eventually tip, but the pattern here seems to be pretty random. So it doesn't seem like regions that are close by on this attractor also have the same probability of tipping, but you can have very close by initial conditions that tip and others that don't tip. And now zooming further in confirms this. So now we take a small segment here of these initial conditions and further subdivide them, and you can see this complicated pattern here on the right, where there doesn't seem to be any structure of nearby initial conditions having the same outcome of the experiment. And as a reason for this, we think we can invoke the chaotic dynamics of the system. So here's just a schematic. It doesn't involve any actual data of the experiment, where you have an initial attractor that you're sitting on, which is on the top right, and you have a competing undesired attractor that you can tip to, which is this blue dot down here. And now what happens during the parameter shift is that this initial attractor is moving up here, so is the other attractor, and your system states are trying to follow this moving state. But because we're moving at a finite rate, and we have chaotic dynamics, if you take close by initial conditions, they actually have time to exponentially diverge during this parameter shift. And now at the end of the parameter shift, your initial basin boundary, which separate these two states, which was initially this dashed line here, becomes this boundary in between red and blue, has also moved. So that means that initially nearby trajectories might end up on either sides of this basin of attraction, thus making it very difficult to predict whether initially close by system states will be on either side of the boundary. Now, this is one mechanism that could explain the sensitivity to initial conditions and also to sensitivity to this rate. But it could also be that this boundary actually is not a smooth boundary, but is rather a fractal. And we're in a lucky position that we can actually directly check this, because as indicated here, there is actually an overlap of the initial attractor with the basin boundary after parameter shift, which means that if we would take initial states up here and instantaneously shift the parameter, we can directly probe this boundary, which is what we're doing in the following. So we have an instantaneous shift of the forcing parameter, and starting at the bottom here, we again sample the attractor over time, and you can see that not all of the trajectories tip. So we indeed have some kind of intersection of the basins with the attractor, or at least the region that we're sampling. And now if we zoom into a region where we go from tracking to tipping initial conditions, we can see that the picture stays complicated. So we still have a very complicated pattern of tipping and tracking. And if we zoom even further in, you can see that this pattern stays like that. So it's like, at least in the statistical sense, it seems like a fractal basin boundary here, which contributes to the general unpredictability of this tipping phenomenon. Which brings me to the summary. So we demonstrated a rate-induced tipping of the AMOC in a global ocean model by fast increases of North Atlantic freshwater. And this highlights that there could indeed be an even diminished safe operating space, as indicated here in this figure. But moreover, due to the chaotic dynamics and potentially this fractal basin boundaries, well, it will be hard to foresee whether actually a specific scenario in terms of forcing or specific initial conditions will tip or track. So that practically that means that this boundary of the safe operating and the unsafe operating space is actually not sharp, but rather fuzzy, as I indicated here. All right, thank you very much.